Good morning. Today I'd like to take up the topic of defects in crystal structures. We looked at crystal structures and we were dealing with ideal situations, and we'll look at various kinds of defects that are there in materials. But before I do that, let me go back to the previous lecture and make a couple of changes or small corrections. When we were looking at the different lattices that are there, I pointed out there are 14 Bravais lattices. And one of them I couldn't find in between, so I hastily scribbled in, if you notice later on, when we did base-centered tetragonal. Actually, that would be wrong. All right, scratch that out. I wrote down 13, couldn't find the 14th, and we created a new lattice, base-centered tetragonal. So what I'd like to do is to just go back to the list and give you the corrected list of 14 lattices. Just note that the difference is there's a simple tetragonal and a body-centered tetragonal. The one we missed out was the body-centered orthorhombic. Out of the 14, I had given 13, and the one that we missed out is the body-centered orthorhombic. I just couldn't find it yesterday, which one we had missed out on the last class, and so we had made a mistake on that one. Okay, the other thing that I'd like to point out, have you got that? There's 14 lattices. The only one we missed out was body-centered orthorhombic. Now, if you remember, I was talking of the diamond crystal structure, which I pointed out was exactly like the FCC, and except that it had 4 atoms inside the cell. And when the 4 atoms are the same as the atoms that are at the corners of the FCC, we call that the diamond crystal structure. And when the 4 atoms inside are different from the ones at the corners and the face centers, we call those what? The zinc blende structure, right? Now, I pointed out in the diamond structure that it is often written as 2 interpenetrating FCC lattices. What I'd like to point out, I use the word simple here, and that would not be an accurate description of the lattice of this. It is actually FCC. Okay, but the lattice does not consist of 2 interpenetrating FCC structures. That's what I was trying to point out, and inadvertently I mentioned that the lattice is simple cubic. So the lattice is FCC, but the basis is what is different here. And that's what we have to think about. Let me draw your attention to that for a few seconds. I've redrawn our structure here. Okay? You can see it. That the face-centered lattice is there. That means we have the corner atom. Remember, in this particular structure, while I've shaded some and circled others, they're all the same atoms, the same element, basically. Okay? Though just for clarity, I'm showing them differently. We have the corner atoms. We have face centers, which are these darker atoms. And then we have the circled atoms, which are inside the cell. Now, there is a way of actually pointing out, giving some kind of a notation to each of these atoms, and that's what I have done here. You see, the corner atom, if we take this as the origin, okay, and this is the X, Y, and Z, the corner atom then can be denoted as being in the 0, 0, 0 position. Actually, all the corner atoms, in fact, can be denoted simply by 0, 0, 0. It's a matter of where we choose the origin. So basically, I wrote that as 0, 0, 0 positions plus lattice translations. If I go 1 lattice constant in any direction, I will reproduce this, this, and this. And then similarly, I can produce the other 3. So all the corner atoms can be referred to as 0, 0, 0. And if you look back to how many atoms per unit cell calculation, all the corner atoms together contribute how many? 1, because there's a 1/8 contribution, right? So we are simply denoting the corner atom by 0, 0, 0. Excuse me. Similarly, the face-centered atoms, which are shaded dark here, can be denoted by these 3 notations. Half, half, 0, half, 0, half, and 0, half, half. What do we mean by that? I move half the lattice constant in this direction, and then half in this direction, and then, where would I end up? Half, half, 0. Oh, I'm interrupting in the body. Okay, that would be this face here, this atom here. I've gone half, and then I don't go up in the z-axis. Similarly, the others are half, 0, half, and 0, half, half. And the other 3 that are there can be obtained simply by a lattice constant being added to these 3. And again, remember, when we were calculating the number of atoms per unit cell, how many are contributed by the face centers? So in this case, we have these three that are the contributions of the face centers, and this, which is the contribution of the corner atoms. Now we have to account for the other four that are inside the cell. All right? And what we do is that we write that the lattice is the face centered. I have a basis of atoms that are 1/4, 1/4, 1/4 added to each of these. Okay? So for each lattice point, if I add on another 1/4, 1/4, 1/4, I will generate the other four that are inside. Do you see that? Let's take the 0, 0, 0 case. 0, 0, 0. I add 1/4, 1/4, 1/4. I end up with this position. What is that? 1/4. That means this is half, and that's 1/4, 1/4, and 1/4. I get this position. Okay? Similarly, we have 3/4, 3/4, and 1/4. So that would bring me here, here, and here. So these two atoms that are inside the cell are denoted by these two positions. And then I'm going to add another 1/4, say, to this. So that will become 3/4, 1/4, and another 3/4. So 3/4, 1/4, and 3/4, which will give me this atom. And similarly, for the last one, 1/4, 3/4, 3/4, which will give me this atom. Okay? So if we think of the diamond structure as an FCC lattice with two atoms per lattice point, one at the regular lattice position and one that is shifted by 1/4, 1/4, 1/4, we generate the diamond crystal structure. Okay? Okay. Let's go to our new topic that we'll enter into today, which is defects. The structures that we looked at in the last class are ideal structures. We assume that everything is ideal in these cases. But real lattices, or real crystals, I should say, have defects in them. And what are defects? Any perturbation or disturbance of the periodicity of the lattice. Okay? Disturbance or perturbation of the periodicity of the lattice. What defined my lattice was that there is a periodic geometrical arrangement of atoms at certain points. Okay, those were the real the ideal structures. And when we disturb and distort that periodicity by some means, whether atoms missing or whether some other defects of various kinds which we look at, that is what we mean by a defect structure. And these defects significantly influence the various properties of interest to us. For example, the various properties that we can deal with and look at its relationship with defects. Something that you're very familiar with. The mechanical properties of a crystal is significantly influenced by defects called dislocations, for example. In fact, dislocations are postulated to explain the mechanical properties of real materials. I won't go into that since that's not the main topic here. But when we have a real material and we try to fracture it, to break it, the calculated values of forces that were required were much higher than what was seen in reality. And so dislocations came about as a result of trying to explain some of these observed properties. Take electronic properties, for example, which is what we will focus on. The conduction, for example, in electronic ceramics, which we'll take up later in the course, is governed by defects known as vacancies. All right? There are other things too, but one of the fundamental things that govern these electronic ceramic type things is the vacancy concentration in the materials. Another important property that is controlled is the mobility in semiconductors. All right? If you have crystals that have very high dislocation densities, we'll take up each of these defects. Then we have that the mobility is reduced in the material. Let me give another example, very common in all kinds of things, the diffusional properties. There again, vacancies, interstitials, and things like that play a role. And finally, when we come to optical properties, which we won't go into at all, or maybe if time permits, as it relates to electronic properties, I will touch upon it maybe. We have things called recombination centers that are related to various defects in the crystal. If light has to come out, which is what we mean by the optical properties, the optical properties deal with the combination that is recombination that is radiative. That means light should come out, or it could be some other wavelength when we won't call it light, but electromagnetic radiation. But if there are defects, then instead of having radiative recombination, we have non-radiative recombination. So that results in no light production. And if we are trying to make an optoelectronic device, one that actually gives us light, and these kind of defects act as killers and remove the lower the efficiency of that material. Okay. There are two types that we can deal with, some of which are non-equilibrium. By that I mean that they don't have to exist in the crystal. They are results of processing and things like that that introduce various defects. And we have the various types of them, and we can get rid of them by careful processing. What do I mean by that? The existence of silicon, which is the heart of the semiconductor industry at present, in high perfection in the form of crystals where there are no dislocations, is really very, very fundamental to its success. And they're able to grow crystals in the form of big boules, okay, they're called boules, and by various techniques of growth and by carefully controlling the conditions to reduce the dislocation density in the crystal. So practically defect-free single crystal bulk is grown, which is then cut into slices and used in the semiconductor industry as wafers. And if we could not control it, there would be a problem. So these kind of defects like dislocations and twins and many of these things which we'll deal with are non-equilibrium. On the other hand, there are equilibrium defects. Which are vacancies, fundamentally the point defects, what we will call. That means at temperatures above 0 Kelvin, there will always be some point defects in the crystal. You can't avoid it. So if you keep your crystal at a room temperature, there's bound to be point defects in it whether you like it or not. So those are called equilibrium defects, and they exist to establish thermal equilibrium in the system. The non-equilibrium one we can get rid, as I said, by careful processing. An example that will be familiar to you may be annealing. We can anneal out certain defects from a crystal by annealing means keeping it at a high temperature for a prolonged period of time. And if you do that with many crystals, many defects are annealed out, we say. Okay? So these are the kinds of defects, some which are dislocations and all that are non-equilibrium defects. And then we have equilibrium defects that are vacancies, interstitials, basically point defects. Let me classify them. We have zero-dimensional defects, 0D I put, it's not OD, which are basically point defects. And the examples we have are vacancies and interstitials, as I mentioned earlier. Basically atoms that are missing and so on, so they have zero dimension, it's just a point. And then you have one-dimensional defects, which are referred to as line defects as a consequence, which are basically dislocations. And there is a further classification of dislocations, which we will come to. Then we have two-dimensional defects, which are planar defects, or they are sometimes referred to as surface defects because they involve the creation of a surface. And an example of that would be grain boundary, twins, stacking faults, and so on, which we'll take up. And finally, you have three-dimensional defects, which are known as volume defects. They're sort of bulk inclusions. Things that should not be there, huge amounts of it, clustered together in 3D and giving us bulk inclusions. Let's take them up one by one. I'll start with the point defects. Probably should be rather familiar with these things. And essentially, the first example I'll take up are the vacancies, which are missing atoms. Remember, my lattice is supposed to be periodic. Yes, go ahead.
Grain boundary is 3D or 2D?
2D. It's a boundary. It's a surface. Okay? If I fold this paper up and I say this is one grain and this side is another grain, the surface that separates these two, it's not flat as you're thinking of for a surface, but it's a curved surface. It could have all kinds of curvature, but it's still, the defect is restricted to 2 dimensions. It's all lying on 2 dimensions. Now, in reality, a grain boundary may have a 3rd dimension of a few atoms. So we define a thickness for the grain boundary as, being a couple of atomic layers thick. Or it can be thin or thick. But fundamentally, that defect is restricted to lie on a surface. Not a flat plane, that's not what I'm saying, but it's a surface. Whereas a 3-dimensional one encloses a volume. Okay? That means the whole thing in there is a defect, not simply the stuff that is enclosing it. You get the difference? Okay? In dislocation, which is a line, it is just a straight line. That's 1-dimensional. Surface is 2-dimensional. And when I put something inside the surface and that's completely different from what is outside, then I say that's a 3-dimensional defect. That's an inclusion or precipitate or something like that. Okay? Okay. Coming back to vacancies, these are missing atoms. The lattice was periodic. I can just use a grid here that we have on this paper. Many times I will draw the lattice simply as a set of lines like this in the form of a grid without necessarily putting the atoms there, but you can imagine the atoms sitting there. Okay. My perfect lattice has got atoms sitting at each of these points here. But a vacancy is where instead of having atoms everywhere, at some place it is missing. Let's say I skip one there. They're all the same atoms, but one of them is missing. Okay? And that happens often close to a surface. In other words, atoms have got thermal energy at any finite temperature, which means that they can vibrate. They can move from their positions. And some of them may just happen to have enough energy. The average energy is something, and then locally one atom may have enough energy to break a bond. And when that happens, it has gone off somewhere else. It broke the bonds that restricted it to that lattice site, and it disappeared, leaving behind a vacancy. Yes?
But how does that explain the appearance of vacancies close to the surface?
What do you mean? How does that explain?
You said that vacancies generally occur close to the surface.
Yeah, it's easier near the surface. You see, there's less bonding near the surface.
But it can also occur
Definitely. That is why I've drawn it inside. Okay, but imagine that this is the surface atoms. Okay, the bulk atoms have got 4 atoms bonded to it. How many do the surface atoms have? 3. All right. So if it's got to get out of there, it's got to break only 3 bonds compared with something that is sitting inside which has to break 4 bonds to get out. Do you get that? I'm not saying it cannot occur here. In fact, I've drawn it inside, breaking 4 bonds, and it's gone off somewhere. But it is easier at the surface because there are fewer bonds to break. But it can occur anywhere in the bulk. And when that atom has gone back, leaving this void, very often the rest of the lattice sort of shrinks a little bit to accommodate that disappearing atom. And that's why the vacancy volume, just by a dotted line there, is typically smaller than the volume of the atom that has gone off, because the rest of the lattice has shrunk a little bit to accommodate the vacancy there. Okay? So one of them has gone. Now the vacancies can move throughout the crystal. And how does that happen? Basically, if an atom moves here, that means the vacancy has gone in there. And it is this vacancy, the availability of a vacancy, that allows us to explain a number of phenomena related to diffusional processes. Atom can move from here to here very easily because there's an empty space there. And so if we make the atom move in this direction, then the vacancy is moving in this direction. And it doesn't have to be restricted to a linear motion. It could go zigzag all through this crystal. So that's how the easy diffusional path is created. If you have a large number of vacancies, for example, then atoms can easily diffuse throughout the crystal. Now we may have a question, how many vacancies are there per unit volume in a given crystal? And the answer to that would depend on the temperature. Because as we have seen, the process involves a breaking of bonds and so on, which is energy consuming. So I would assume that if I go to a higher temperature, I have more vacancies. I can make a safe assumption on that. And it is seen that the number of vacancies per unit volume, if we denote that as NV, the number of atoms per unit volume in the lattice lattice atoms, we denote by N. Then we have that NV is equal to N exponential minus EV by KT. What is EV? It's the formation energy for the vacancy. All right. Typically, when we see the term KT in an equation that involves atoms and things like that, we know that it is telling us something of the measure of the thermal energy of the system. The higher is KT, the more thermal energy the system has. Right? K is joules per Kelvin, and this is Kelvin, so that's a measure of how much joules are there. And EV is the formation energy for the vacancy. To give you an idea, for example, N we should be able to calculate the number of atoms in the lattice per unit volume. How would you do that? I know the number of atoms per unit cell. I know the lattice constant for the unit cell, from which I can calculate a volume for the unit cell. And based on that, I should be easily able to calculate the number of atoms per unit volume for that. Is that clear? Right? So if we take the example of silicon, for example, it's something like 5 into 10 to the power 22 atoms per centimeter cube. Roughly. Now most solids will have something like this, 10 to the power 22 kind of numbers. Okay. And we can guess then, looking at this equation, that as we increase the temperature, this term increases, this term decreases. Right? The lower part, this term is increasing, the exponential term is increasing, and so we have an increase in the number of vacancies. We'll look at that. So ultimately, the whole process is related to a thermal activation. If I give enough energy, the bonds will break, and we will get the formation of vacancies. We may think of it in terms of an energy barrier. If I plot energy, there's an atom sitting in a particular lattice site. If it breaks free, it can go somewhere else, either in the form of a vacancy or we'll see some of the defects, or it may leave the crystal. But to do that, there is some sort of an energy barrier that it has to cross. And that is fundamentally what we have defined earlier as EV in this equation. How much energy will it take for this vacancy to form, for the atom to break its bonds and go away from the crystal? Most of the equations of the kind that we just looked at are referred to as Arrhenius type equations. You may be familiar with that term. And when you see an Arrhenius type equation, one of the first things you can immediately do is to make a plot of the log of whatever is the rate that is being spoken of. So in this particular case, the log of this versus the natural logarithm versus 1 by t. So we can rewrite this equation. Before I draw that, I'll do that. The log NV is given by the natural log of n minus EV by kt. Simply taking the logarithms. Right? So what I can do is, if I plot the natural log of this term versus 1 by t, what would I expect? A straight line. Basically, that is a y is equal to c minus mx type of term. So I will get a straight line with a negative slope in this case, where it intercepts the axis, gives me the natural log of n, and then the slope gives me what? EV by k, basically, right? I get the slope from, I know k, which is Boltzmann constant, so I know what is the activation energy for this process. So if I ever have equations of this form and I don't know what is the activation energy, if I can experimentally determine this term as a function of temperature, I'm able to calculate the activation energy. And that's what we do in practice. Experimentally try to determine various processes like this, whether it be vacancy concentration or other things that are described by the Arrhenius equation. As a function of temperature, we determine the property to extract activation energy. And when we know the activation energy for a certain process, we can comment then about possible mechanisms for that process. So it's an unknown process happening. I see the activation energy calculated out, and then I say, oh, it may be related to this behavior or this behavior. So this is a very important technique that allows us to understand what is really happening in that material. So we are able to calculate out activation energy. Let's take the case, a practical example of aluminum. And I want to know at a given temperature how many, what is the vacancy concentration. So the way to go about this is very simple. I make use of a block of aluminum that I can heat to various temperatures. And what I do is I measure the length, the change in length at various temperatures, which I can physically measure. So as I get delta L by L, which is a macroscopic measurement for the block of known length L, I measure the change in length at different temperatures. So as a function of temperature. I can also do something else. I can take the X-ray diffraction at various temperatures for a heated block of aluminum. And from that, what do I get? For any given X-ray diffraction picture, I will get peaks depending on the structure. And what I get here is intensity versus 2 theta. And we won't go much into it, but just to illustrate the point, I get some 2 theta values for the different peaks. And then using the Bragg condition, we evaluate what are D's. Okay? And from which then I can calculate the lattice constant. D is the spacing between any given set of planes. A is my lattice constant. And there are geometrical relationships that relate D and A. For example, 1 by D squared is equal to H squared plus K squared plus L squared by. So, what is it? Which is what I've written, plus. Oh, there's a plus missing here. Oh, very good. Okay. I warned you, I miss out pluses and minuses all the time. So, if you have a relationship like this, from your X-ray you got D, you know what H scale value this peak has, you can calculate A. and you do this for different temperatures, what do you expect? As you heat up the block, will D change and will A change as a result? We will. Remember, I showed you the curve, the energy curve, the asymmetry, right? We looked at this and we said that because of the asymmetry, we have the change in the mean position. You recall this? So microscopically, the atoms are sitting on an average farther apart at higher temperatures, and that is going to determine the lattice constant. So from my X-ray diffraction, I can also get delta A by A, which is the change in the lattice constant compared with the my reference lattice constant at room temperature. And we can then plot these two as a function of temperature. Delta L by L, which I got by macroscopic measurements, or delta A by A, which is the change in the lattice constant that I've got from X-ray. And when we plot this as a function of temperature, what we see is that instead of these two, we would expect that they follow the same trend, right? One expansion should, at a microscopic level, should be the same as that at the macroscopic level. But what we see in reality is that the delta L by L may look something like this, whereas the delta A by A may look something like this. There is a finite, small but finite difference between the values that we obtain by the macroscopic measurement and what we see, the microscopic change from XRD. And this increases as we get closer and closer to the melting point of aluminum, roughly 650 degrees centigrade, somewhere there, right? So the closer you get to the melting point, the more is the difference between the macroscopic measurement that you've made and the microscopic measurement from the XRD. And fundamentally, this is related to the formation of vacancies. The lattice constant that I'm measuring is an average value and therefore is not affected by the presence of vacancies. The X-ray can't detect it. So it gives me the true lattice constant and does not account for vacancies there. Whereas the macroscopic measurement, how much has the block actually expanded, is going to tell me how many vacancies are there. And so at a given temperature, I note the difference here between these two. Now I have then a vacancy concentration as a function of temperature, which I can then go ahead and plot in my Arrhenius form as versus ln of the concentration versus 1 by T, where I'll get my slope, and from which I calculate for aluminum what is EV. Okay? So experimentally, I can go ahead, determine vacancy concentrations at different temperatures, and then plot this term to extract the answer. And in the case of aluminum, it turns out to be something like 0.6 EV. So it requires about 0.6 EV per atom to create a vacancy in the case of aluminum. On the other hand, in the case of silicon, we require much higher values if you do a similar kind of experiment, and it's of the order of about 3 EV. These are all approximate numbers. I don't recall the exact values, but 2 to 3 EV is the kind of values we see, and we see that difference. You see, one is covalently bonded and one is a metallic bond, and things like that. So there are differences that come about even from bonding, what energy is required to create the vacancy. I'll point out here also that, again, in metallurgy you're more familiar with it. I can take it to a high temperature where I have this high concentration of vacancies. So I can calculate what will be the concentration at, so 1 by T means temperature is increasing in this direction. So at some high temperature I have this value. And if I cool it down very slowly, as I come to a lower value of temperature, I will have this number. But what happens that if at this temperature I quench it? Quenching, sudden cooling. And then I bring it back to room temperature and I measure how many vacancies? Much more vacancies than what I would expect by equilibrium cooling. This was a slow cooling that got me here, because those vacancies did not have time to get out of the system. So by quenching, I can artificially create structures that are not equilibrium and play with the properties by things like quenching. Okay? We won't go into that, but just to point that out as in passing. The second category of point defects itself are what are known as interstitial defects. Excuse me. And basically the word interstitial means it's gone into the interstices. Between the atoms it has gone. And we could have the case, a very simple example of a self-interstitial, where I have the lattice and one atom decides to go in between there. In the case, later we will see this as a particular. So instead of being here, it has gone into an interstice. Any of these are called interstices. So it sits at this interstice. This is a self-interstitial. By itself, a lattice atom, a host atom in the lattice, has moved from its regular lattice position into the interstitial. But more commonly, what we find are impurity-related interstitials. That means instead of the host atom, I have another atom that is sitting in the interstitial position. Something else has got in there. Okay? And this host atom, the interstitial atom may be smaller, typically, otherwise it's not going to fit in there. Right? And you find the example of carbon in iron. Typically, you will get interstitial carbon like this small atom of carbon sitting in the lattice of iron. And similarly with interstitials, we can associate an energy of formation EI and use a similar equation as before. The formation of the concentration of interstitials related by a similar term, except now my energy of formation is EI, which is different from that for a vacancy. A similar equation. The third kind of point defects are substitutional. And in this case, the impurity atom replaces the host atom. All right? In the case of interstitial, I had an impurity, but it did not disturb the positions of the host atoms. But in this case, in the case of substitutional, as the name implies, I am going to substitute for the host atom. All right? I'm just drawing a small part of that lattice there. So a foreign atom sitting in here that has replaced the host atom. Now as I've drawn it, the substitutional atom could be larger than the host atom, or it could be smaller than the host atom. Okay? In this case it is larger than the host atom. In this case it is smaller than the host atom. Both these possibilities are there. And when we talk of dopants in semiconductors, which we will come to, dopants to be active electronically cannot be sitting at interstitial sites. Okay? Dopant atoms replace in one of these configurations depending on the size of the atom that is replacing the host atom. So typically dopants, for them to be active in semiconductors, will be a substitutional defect, giving us an additional electron or a lack of an electron. There is a special category, compounds and things like that, but particularly for ionic crystals, these are all similar atoms. I've showed you sort of like elemental cases. They're all same. But in the case of compounds also, we'll have similar kinds of defects, except now we have more than one kind of atom as part of the host lattice itself. Okay, say the zinc blende structure, I've got zinc and sulfur. They're all part of the regular lattice, or the silicon carbide, silicon and carbon, gallium arsenide, any of these. But in the case of ionic crystals, we have to be careful of something. We need to conserve the charge also. Remember, the ionic crystal consists of charged species. There are cations and anions. So I can't simply get rid of a lot of the cations, leaving my crystal negatively charged. If the positively charged ions, a number of them are removed, I'm left with a crystal that is sitting here negatively charged. It's not going to just remain there negatively charged. So I have to conserve the charge. And in this case, we generate two special types of equivalent to what we saw earlier, the Schottky defect, where one anion and one cation, one positively charged and one negatively charged ion, are missing. So it's like a big vacancy. Both the anion and the cation are missing. Similar to the idea of the vacancy we saw earlier. But because both are missing, we are conserving the charge. The other is what is known as a Frenkel defect. One of the host ions, okay, it could be either the cation or the anion, is displaced to an interstitial site. Okay. So I got cations and anions in the system. Either one of them could move. So I'm not removing any charge, I'm just displacing it into, and that is similar to the interstitial that we saw earlier, and not change the charge at all. Now, I commented that it could be the cation or the anion. Which do you think is more likely, and why? Pardon? Cation. Why?
Because they will be smaller in size.
All right, very good. I'm going to fit something into an interstice, and so if I to draw it, I've got anions which I will draw as larger, and cations that I'll draw as smaller, because typically cations tend to be smaller than the anions, as we saw earlier. And the reason why the anions are unlikely to move into interstitial site is they are larger. So it's harder to push something into a small gap when you have the option of a smaller ion moving into that gap. So if you draw it, the lattice, it will look something like this. A series of positively and negatively charged ions. And we can take one of these and move them into an interstitial position. So if I draw that properly, we have, if the case of the missing, the Schottky defect, I will have, let's say, this ion is missing, one cation is missing, and one anion is missing. Okay? And that pairing is known as the Schottky defect. All right? And this, if we look for the Frenkel defect, you would then put in these. I'll draw that again for you. The Frenkel defect will look like, oh, sorry, we missed there. That's a cation. Okay, the negative charged ions I'm labeling. One of these positively charged species has moved out, giving me the Frenkel defect. All right? I could also have substitutional defects, substitutional or interstitial impurity defects in the ionic case. Again, the overall charge neutrality needs to be maintained, and in this case, if I put in substitutionally a species which has got, say, a higher charge than the host, then one more host ion has to go missing. What does that look like? For example, in a where the cation was sodium, if I replace one of them with magnesium that has got charge 2+, then to maintain the neutrality, one more sodium ion has to be missing from the system. Okay? So we can create a lattice as before, except that if I replace this with a charge 2 species, I would have to get rid of one of these. You get the point? To maintain the charge neutrality, instead of sodium with single charge, I put a doubly charged ion there to maintain my neutrality, there will be a associated sodium ion missing from the system. So that's in the form of substitutional. The same would apply with interstitials also, where we can have charge conservation by the formation of vacancies of one kind or the other. Here's some other possibilities in compounds for defects. I should say one other, I will not go much into this. Anti-site defects. What do I mean by anti-site defects? When I've got two species, for example, sitting in a lattice, and I label the positions where each of them sits as A, B, A, B, or let's call it all this way. What happens if for some reason during growth, one B atom, instead of sitting in the B position, decides to go and sit in the A position? If they are of similar size, that can happen, right? It's a defect. It shouldn't go there, but for some reason, it ends up sitting here instead of in its own site. Locally, there is a switching of sites as a defect, and that is called the anti-site defect. In the case of elemental materials, which are elements, that possibility doesn't arise because all of them are the same. So whether it sits here or here, it doesn't matter. But in the case of compounds, I have the possibility that instead of sitting on a regular site where it should sit, say corners it should sit, instead of that it went and sat in the face center. And the one that was sitting in the face center switched to the corner. That would be referred to as anti-site defects. Okay. We have covered the point defects, which are zero-dimensional. I will start line defects. I probably will not be able to complete it today, but we will take it up for now. These are one-dimensional defects, and as I pointed out, they are non-equilibrium. Typically, they are produced by stress. So I can externally apply stress to a crystal and produce dislocations. A very simple example, if you take a wafer of silicon, very clean, pure, hardly any defects in it, and in the process of handling it, you hold it with a tweezer, all right, a metallic tweezer. So this is my nice little silicon wafer, and I put the tweezer on it like this to take it somewhere. Right under where I put the tweezer, we've gone and generated a host of dislocations. Because in the process, particularly there are the formation energy of dislocations for different materials. If it's a softer kind of material, just the very act of pressing it there to take it from here to here, I've already gone and destroyed it. So in commercial processes, nobody will be sitting there handling it with tweezers. Many of these are vacuum chucks and things like that allow you to remove a wafer like this without ever putting pressure. The vacuum holds it and takes it, or other such techniques are used. But simple stress on crystals are sufficient to create, this is externally applied. Now this can also happen during growth. For various reasons, crystals can end up with dislocations. I'll give you a simple example because again I don't want to go much into this, something called misfit dislocations. Suppose I take a crystal whose atoms are spaced this far apart. And I tried to grow on top of it another crystal, which I can do, which we will call heteroepitaxy in this case, where this one's lattice constant is this far apart. All right? And I'm going to grow, there's a sequence, I mean it goes on higher. This is bulk, very thick, and then there is a little bit of this layer I'm growing. When this layer is growing here, what will happen? Here the atoms want to sit this far apart, and then I'm going to try to put something on it where the atoms want to sit this far apart. I'm going to generate stresses there. And up to a point, that's known as a critical thickness, this crystal will accommodate and change its dimension. The lattice will change. The constant will change. Why will this not change very much? Because this is bulk. It's harder to deform something that is thicker than something that is very thin. So my film will be stressed. And as a consequence of that, I will have them sitting more or less accommodating what the substrate. But beyond a thickness, that stress will be so high that eventually this will start sitting at its own spacing this far apart. Periodically, to account for this change in lattice, it will introduce some kind of a dislocation. Very regularly, it will introduce a dislocation. These are called misfit dislocations because they accommodate the misfit in the lattice between the film that is being grown and the film that is at the bottom. And the substrate that is at the bottom. And all these dislocations, a periodic array, will lie in this plane. So I've got this growing on top of this, and the dislocations all lie at the interface. So the misfit dislocations lie just at the interface. So these are called misfit dislocations and are produced either by during growth, and then there are other dislocations that are produced by stresses in the crystal. There are two types of dislocations we can take up. Again, this is familiar territory: edge and screw dislocations. In the case of edge dislocations, it is best understood perhaps as an extra half plane of atoms or a missing half plane. So I got these planes of atoms. Most of them go down further, but some of them, one of them, say, terminates here. Something like this we will see. Okay, this is supposed to be all equally spaced at the bottom, and here also. But around this dislocation here, we have a region that is different. And if you look at it, the portion above here, they are compressed. Okay, somewhere in this area, the planes are being pulled closer together, and out here, they are being spread out. So there is a very strained region that is associated with the presence of this dislocation. The symbol that we use for the dislocation, edge dislocation, is an inverted T like this. And when I refer to the term, the line of the dislocation or dislocation line, we will be talking about this line that goes into the paper. Okay, so it is going in. So my dislocation line is into the plane of the paper here, and my symbol is this, and that represents the extra half plane that is present there. And as you can imagine, it is very easy for this extra half plane to move. Okay, it just flips here, then the extra half plane is here, and then the next one flips here, the extra half plane is here. So at the end of all these motions, I will end up with something like this. It has moved to the edge by this motion and leaving me with a step here. So if I look at the crystal there, there is a extra plane sticking out there. And if I draw that in 3D, and I will come back to this later because it's important. Okay, there is this extra step that is created here, but the dislocation line is into this. Okay, and this is what is referred to as the edge dislocation. We will take up the other little more about edge dislocations. How do we characterize it, and what is the strength of the dislocation? We use a term called Berger's vector and things like that.